even if two molecules have the same molecular mass, and so have the same, the molecular ion peak in the same place, you can still use mass spectrometry to tell the difference between them, because the fragmentation pattern of the rest of the peaks will be different in the two molecules. And so you can tell what sort of branches might have come off of different molecules in order to produce those peaks. And they'll be different for each molecule. Now, common branches are methyl groups, common branches that break off of molecules when they pass through that high energy beam of electrons that you're shooting at the sample, as we discussed in the video on the concept of mass spectrometry. Common branches that are kicked off when a molecule gets hit with an electron are a methyl branch, an ethyl branch, so CH2, CH3, and these are branching off of the molecule. And also even a propyl and a butyl branch. Now, for our purposes, the propyl and the butyl branch are not ones you'll need to memorize for the test or remember for a test. But you should remember the methyl and the ethyl branches. So notice a methyl branch has one carbon, that weighs 12 AMU, and 3 hydrogens, each weighs 1 AMU, so that's 3 total. So the mass of this methyl branch is 15. And so when a methyl group gets kicked off of a molecule, you'll have a peak that's 15 mass units lower than the molecular ion peak. So this capital M is standing for the molecular ion peak. And because a methyl group got kicked off, and a methyl group weighs 15 mass units, you should have a new peak that's 15 lower. So if somewhere in a molecule there is a methyl branch, then that branch is going to get kicked off by those electrons, and you'll have this M-15 peak. Similarly, an ethyl group has 2 carbons, so we have carbon and hydrogen here. 2 carbons, each carbon is 12, so that's 24. And it has 5 hydrogens, each hydrogen is 1, so that's a total of 29 mass units, AMU, in an ethyl group. And so, if a molecule has an ethyl branch, then the electrons at some point will knock that branch off, and you'll get a peak that's 29 mass units lower than the molecular ion peak. So you've got the molecular ion peak, and this is the mass of the ethyl group that's getting kicked off. And so you can use these common patterns of branches that get kicked off of molecules in order to distinguish between molecules. And you'd only need to do this if the molecules had the same molecular mass. Otherwise, you'd just use the molecular ion peak all by itself. So for example, here it says the following are mass spectra for constitutional isomers. Iso means the same. Mers means parts. So isomers are things that have the same parts. If they're constitutional isomers, they have the same atoms, same type, same number. They're just put together differently. If they have the same parts, same number, same atoms, if they have the same molecular formula, in other words, then they should have the same molecular mass. And so we're going to get the same molecular ion peak in both of these things. And so we're going to have to use these common fragment patterns to distinguish between them. So they give us 2 constitutional isomers. The first one is ethyl cyclohexane. So that's cyclohexane with an ethyl group coming off. So this is ethyl cyclohexane. Remember, hex means 6 carbons. I knew to put them in a ring because there was the cyclo in front. Cyclo means put it in a ring. AN means all single bonds, and E means there's no functional group on that. And then for the branch, F means 2 carbons, and YL just means it's a branch. So that's ethyl cyclohexane. The other constitutional isomer they give us is 1,1-dimethyl cyclohexane. Okay, so cyclohexane, So 1,1-dimethyl cyclohexane. So the cyclohexane is really the same. We have 6 carbons and they're going to be in a ring. 6 because hex, ring because cyclo. All single bonds because AN, and there are no functional groups. We know because there's an E at the end. This 1,1 just means that these 2 methyl groups are going to come off of the same place, the same carbon, carbon number 1. And the prefix meth means there's just 1 carbon in that branch. So you'll have 2 1-carbon branches coming off of the same place. All right, so you'll notice both of these molecules have 8 carbons. And they have, if you count them all up, they'd have 14 hydrogens. And so they have the same molecular mass, and they would have the same molecular ion peak. So you won't be able to tell the difference between them just by looking at the molecular ion peaks. Oops. You notice, it looks like there's the molecular ion peak in both of these is at around 112. So instead, what you can see is that they have different types of branches on them. In this ethyl cyclohexane, you have an ethyl branch that could easily get kicked off. And in 1,1-dimethyl cyclohexane, you have a methyl branch that could easily get kicked off. If this ethyl branch gets kicked off, then the molecular mass of the molecule, which looked like it was around 112, that molecular, wherever that molecular ion peak is, the new you should have a new peak minus, oops, for ethyl, minus 29. Because an ethyl branch weighs 29 AMU. And for this other molecule, 1,1-dimethyl cyclohexane, if a methyl group gets kicked off, then wherever you have the molecular ion peak, you would subtract the mass of the methyl group that gets kicked off. The methyl group has a mass of 15 AMU. And you should have a peak at that new position. So, if we take our peak in this left spectrum, our molecular ion peak as being the most significant peak at the far right of the spectrum, that peak at 112, and if you wanted to check that, you can figure out the molecular mass using these formulas. It should give you around 112. So you should have that molecular ion peak, and if it's the ethyl cyclohexane, then we should have another peak that's 29 mass units lower than that. So 29 mass units lower than that. 20 mass units lower than that would be 92, something like right here. That's 20. And then another 9 would be around 83. So that would be right here. And you notice we have a big peak there. So this left spectrum has an M-29 peak. So whatever that molecule is, it has an ethyl branch somewhere. That's what's causing this new peak. Does it have an N-15 peak? Well, we go back to the 115. 10, that would be around just 102. And 5 more would be around 197. There's not a significant peak at the -15 position, so probably this does not have a methyl branch anywhere. So already we're getting the sense that this is the spectrum for ethyl cyclohexane. This is the molecular ion peak minus the 29, in other words, minus the ethyl group. The molecular ion minus the ethyl group. Compare that with this spectrum on the right. Here, our molecular ion peak is pretty small, but it's at the same place, around 112. And here, if you subtract 29, so 20 would take us to here, and 9 would take us to around 83, you notice we don't really have a peak there anymore. So there wouldn't be any ethyl branch that would be kicked off of there. And if you, right, we didn't have the M minus 29, so an ethyl branch wouldn't have been kicked off. If you wanted to check for a methyl branch being kicked off, you would go to the molecular ion peak, subtract 15, so 10 would take us to around here, and 5, another 5 would take us to around right there. And we have the M minus 15 peak. This here is the molecular ion peak, and this is that molecular ion minus 15 peak, where 15 is really that CH3 that got kicked off. And so, because this one on the right does not have the M minus 29 peak, but does have the M minus 15 peak, it must have been the structure that had a methyl group that could have gotten kicked off, a methyl branch that could have gotten kicked off, and so it must have been 1,1-dimethyl cyclohexane. So 1,1-dimethyl cyclohexane. Okay, so what did we do in this exercise? We had two molecules that had the same molecular mass, so we couldn't use the molecular ion peak to distinguish between them. So instead, we saw what types of branches were in the molecules, ethyl versus methyl. And we noted that those branches can easily get kicked off. And when they do, a unique amount of mass is kicked off of the molecule. And so, if a molecular ion peak minus that specific mass is indicative of that specific branch. So we looked for peaks at those positions in the two spectra, and we saw that the M minus 29 peak was only on the left, so only that would have had an ethyl group. M minus 29 is the ethyl, and the M minus 15 peak was only at the right, so only that had a methyl group. So this is just looking for common branches that get kicked off, looking for peaks related to those, away down to the left of the molecular ion peak.